So let me share my screen. Okay. Okay. So this is the second part of the subject area we started last week. Last week, we mainly talked about advanced manufacturing methods to produce advanced materials or functional surfaces. So today, we're going to the second part, in which we will show several functional surfaces serving different functionalities most of the time, with a common, let's say, point that all of them incorporate a kind of micro nanotechnology. So let me pass to the next. So the inspiration in all this came from nature, as in many things, as in many other things. Here I have some representative examples of insects, animals, or plants that incorporate this kind of micro and nanotechnology. So scientists were observing some strange behavior in several plants or insects, and then when they studied them carefully, they saw that this kind of objects incorporate micro and nano features. So a lot of effort has been done in order to mimic, let's say, the nature behavior or the nature properties. Starting from the water strider here, you can see that when when this insect is able to walk on water, this happens because its legs have micro nano features on them. So there is air trapped inside its legs, and that's why it can defeat, let's say, surface tension and can stay on water. If we go to this example, here we see the Salvinia plant, which is a plant that can sustain several waves inside water without being destroyed. If we carefully look it under a microscope, we will see that it has some hydrophilic parts and some superhydrophobic parts, which allows them to flow with the water flow and not be destroyed. Another example is the desert beetle, in which we can see that this kind of beetles can live on very dry areas. And how they collect the water is this way. All of its back and its legs are covered with nano features that collect efficiently water, and they can drink the water existing in the atmosphere without being able to be in a lake or in a river. And of course, the most famous one, which is the lotus leaf. Here we can see that a lot of leaves that stay on top of small lakes, etc., they are usually very clean. This happens because these leaves have micro nanotopography on them and low surface energy, and they can self-clean by using the water rain. So one important functionality from which several others can be extracted is the wetting control. Starting with the definition, we consider a surface as a superhydrophilic one when water can spread evenly on the surface topography. So you can see here I have a drop of water that is spread all over the surface. Whereas there are several other states like the Wenzel state, in which we have intermediate wetting and some part of the drop is pinned on the topography, but there is a spherical shape of the drop. And of course, we have the Cassis state, in which the drop is completely, let's say, spherical, can easily move on this kind of surfaces without any friction. And you can take advantage of this kind of situations to have the self-cleaning effect we talked earlier. So in order to characterize a surface like this, you need two things as metrics. One is the water static contact angle, which is the contact angle as the drop is placed on a surface. And the second one is the hysteresis, which is actually the highest angle that I can measure on a surface by increasing the volume of a drop, and the lowest contact angle when I'm decreasing the volume of the drop. So by probing neighborhood, let's say, areas on the surface, I can have this dynamic range of measurement, which is called hysteresis. And from this, I can understand the adhesion of the liquid with the solid. To achieve wetting control in any state of this, I will need two things. First of all, I will need a type of micro and nano topography. This topography can be random, like this one, can be ordered like this one, or can be ordered like this one, but with higher features, let's say. And the second thing that I will need is to have tuned chemistry. So if I want to be like this, super hydrophilic, and collect the water and absorb the water, I should have a hydrophilic material on top of this topography. Whereas on the other hand, if I want to go to this state, to the super hydrophobic one, I will need a low surface energy material, a hydrophobic material like this one. So if I use a topography, micro nano topography, and the hydrophilic material, I will take something like this. So easily the water will be absorbed on the surface. Whereas if I go to the other extreme, which is the super hydrophobicity, we will see that drops will roll off easily by the surface without any interaction with it. So by controlling the topography and the surface chemistry, I can control the wetting properties of the surface. Of course, this field is not a new one. From 1950, let's say, Wenzel first in 1936 and Cassie and Baxter in 1944 established the models about wetting on rough surfaces. Since then, a lot of achievements have been made. For example, in 1997, it was the first observation that the lotus leaf has this topography that I showed you in the earlier slides. In 2003, the first superhydrophobic surfaces were made on plastics. Then in 2007, we expanded our knowledge and we were able to design surfaces that repel not only water, but also other liquids like oils or reagents, which have much lower surface tensions. And from that time until now, a lot of effort has been given in order to produce surfaces with controlled wetting properties that can have this sustainable performance over time. So some people propose self-healing materials that even if they get destroyed, they can be renewed. Other people worked on how to achieve other functionalities coming from the wetting properties control, like the antifogging surfaces here. How we can use this kind of wetting control on other phenomena, like the condensation on, like the phase change phenomena and the condensation on this kind of surfaces. And of course, nowadays, everybody is trying to make multifunctional materials that serve several functionalities and can also be durable against time, against mechanical stresses, against everything. So we want to pass this kind of technology to everyday products, sorry. And why this? Because the use of this wetting control can provide new products and new materials, advanced materials. For example, we can prepare super hydrophobic membranes in which the water desalination happens much easier and much more effectively. We can have surfaces that can transfer heat in a much higher rate compared to normal surfaces. Here you can see that by making the phase change phenomenon of condensation in drops instead of films, I can gain orders of magnitude higher heat transfer capabilities. Of course, I can tune fabrics or other membranes to absorb or repel water or other liquids according to my needs. And of course, I can incorporate these kind of surfaces into new devices and produce new diagnostics for food, health, environment monitoring, for a wide range of applications. And of course, I can create antibacterial surfaces, antifungi surfaces, and surfaces that can be used, for example, in food science, in packaging, and extend the shelf life of the product, or it can be used in general, let's say, in surfaces of general interest and have less contaminations. And of course, I can do food packaging that can repel or reflect sunlight, can stop moisture, can stop a wide range of different probes that affect the food quality. To do so, nowadays we're able to, by having the appropriate tools, as I showed you in the last lecture, nowadays we can tune and design on demand the topography that we have in this kind of surfaces. And knowing the liquid properties, I can also pre-design and pre-estimate what will the behavior be of a specific type of topography. So for different topographies, we have different equations that can be easily applied and know before I fabricate the surface, the properties that it will have. Some of the methods coming from micro nanotechnology that are used in order to produce this kind of functional surfaces are, as I said before in my first lecture, plasma processing, the combination of plasma processing with lithography or colloidal lithography, of course, hot embossing, and every replication technique that I have a template and I press it with pressure or with UV. Several techniques exist in order to have a specific design. So let's go with the plasma processing. Here you can see that I have a cycloolefin polymer, which is a type of polymer which is initially hydrophobic, and depending on the etching time, I can have different topographies created on this same material. So we have small features for surfaces treated for a short period, which grows larger and becomes more complex as etching time increases. And the nice thing about this thing is that although due to the plasma processing with oxygen gas, which makes initially the surface hydrophilic, after some time, super hydrophobicity is restored, and then can create a super hydrophobic surface without adding any top layer. So depending on the application, I can choose to have this kind of topographies either hydrophilic, if I want to bind something like here, in which we have a high binding surface for proteins, or I can add an extra layer and have a super allelophobic surface. The same can be done in other materials. Here is PIC, which is a ketone. Here is an acrylic type of material, PMMA, and here is an inorganic polymer, PDMS. So by applying, again, this powerful technique of plasma processing, I can create a wide range of different topographies on this kind of material. And as you can see here, I can repel very easily water, but also oils and reagents. And here we have the behavior of a soya oil drop on this kind of surface. Soya oil has much lower surface tension value, which makes much more difficult for a surface to repel. But you can see here that even for this kind of liquids, the surface remains unwetted. Okay. Now, if we combine the etching technique with lithography or colloidal lithography, which is the method, as I said in the first lecture, to create a uniform monolayer of nano and microparticles on top of the surface, like the ones you can see here, I can create this kind of pillars or this kind of pillars, and by tuning the etching parameters, I can have vertical pillars like the ones here, or pillars with undercut like the ones here. And by doing so, and by taking advantage of the possibilities and adapting the profile of the topography, I can repel very easily either hexadecane. Hexadecane is a much lower surface tension liquid compared to soya oil. And here you can see that by tuning the profile of this kind of pillars, which exist on top of the surface, I can have repulsion of hexadecane drops easily rolling off this kind of surfaces. So although wetting control for water as a liquid is easy, if we go to other liquids like oils or reagents, you need to have a very nice and pre-designed shape of the structures. You cannot easily have a random topography having this behavior. So nowadays we can easily use different tools existing and create the profile we need depending on the application. Here I'm showing you another publication about how to create surfaces that can repel water again, but also high-speed water drops hitting the surface. So in this work, we had a laser beam focusing on a donor substrate covered with a liquid, and this laser beam created a jet. This jet hit the surface with a very high velocity. And you can see that depending on the pressure, we can have stability of this wetting behavior up to 35 atmospheres. 35 atmospheres, to give you an estimate, is several meters, several hundred of meters below the surface of the sea. So you can easily, by tuning the topography of the surface, have a very robust surface that can sustain high impact drops. And here you can see a scanning electron microscope image of the surface and the nanopillars we had on this kind of surfaces after the laser hit the surface. So you can see here that the pillars were not destroyed because the lower, let's say, the size of the pillar, the higher the number and the density of the pillar. So the liquid equally distributes the pressure against several pillars, so the mechanical effect and the destruction of the pillars was not possible. Here I'm showing you another application in which we want to have surfaces that can respond as hydrophilic or hydrophobic depending on the voltage applied between the liquid and the surface. This phenomenon is known as electrowetting. So here, by tuning the pillar's profile, but also the thickness of the dielectric layer between the pillars and the silicon wafer, you could have reversible or irreversible changes of the coatability. So by using this thin dielectric layer, you could have irreversible wetting modification. So if you apply the voltage, then the drop shape changed, the surface was wetted and stayed like this, even if I turned off the voltage supply. Whereas when I was using a thicker dielectric layer, by turning on and off the voltage supply, I could achieve reversible wetting. Other applications of interest using, again, the same starting point, which is the wetting control, is the friction control when liquids move on this kind of surfaces. So in these two publications, we showed that if we use a super hydrophobic surface that is really robust, even if we use a very viscous liquid like glycerol, the drops of glycerol could easily be moved with minimum, let's say, force applied on them on this kind of surfaces. Whereas when we used the untreated ones, the value of the force required was much higher. So this kind of surfaces, the super hydrophobic ones, exhibit very low friction force values and friction coefficients. So they are ideal surfaces for moving liquids over long distances or having them on surfaces that are in contact with liquids and we need to have lower friction. Of course, another property that is coming again from the micro and nano texturing of the surfaces, the control of the optical properties of a surface. Here you can see an untreated glass, let's say, and here you can see a glass that has micro and nano textures on it. In this kind of applications, if we manage to have very small texture, which is below, let's say, 300 nanometers, our eye cannot see it. So even if this surface is textured, we cannot observe it. So we can see it as transparent. But by texturing it, we also achieve to reduce the reflection made from the light hitting on the surface. So if we have this nano texture, we have transmission, and the light that is reflected is much lower compared to the untreated glass. So by not changing, let's say, the transparency of this kind of surfaces, we manage to make them anti-reflective. And of course, this is the technology that is commonly used in all the electronic devices we have, in the screens of our PCs, in the screens of our mobile phones, etc., in order to reduce the reflection that is happening from the lights. Another optical related application is the one I'm showing you here, in which, again, without destroying the initial properties of plexiglass, we managed to have a glass that, even if it is exposed to a flow of humidity, it doesn't become blurry. So the water is absorbed and creates a film, a homogeneous film on top of this nano-rough surface. Because the reflective index of the water and the material is really close to each other, you cannot see a difference. So by measuring the transmittance, we saw that the super hydrophilic surfaces with very low topography was able to maintain a very high transmittance rate even after several minutes of exposing it to humidity compared to the other types of surfaces tested. So by tuning the wetting properties of a surface, you can also make antifogging surfaces or even anti-icing surfaces, surfaces in which ice is not easily formed or it is easily detached. And of course, as I said in the beginning, you can also use this kind of topography to enable dropwise condensation instead of filmwise, sorry for that, and increase the heat transfer coefficient of this kind of surfaces. So by making them rough and super hydrophobic, instead of having a film formed on this kind of surfaces, we have drops. In this way, if the size of the drop is reduced, let's say, from 2.8 millimeters to 110 micrometers, by using this rough topography, you have a 200% on the heat transfer coefficient. And if we want to visualize this difference, it's shown in these videos. So here we have an untreated surface, and you can see that we have very large drops that are barely movable between places. Whereas when I use this super hydrophobic surface, you can see drops are moving, empty gaps are again and again covered by new drops. So in this way, you have an accelerated effect of the heat transfer. And if we see a cross-section, we can also see here's a surface, and we will see that when humidity comes with contact on the surface, it creates highly mobile surfaces that can also jump. Gravity is this direction, so we can see some drops coming and jumping off the surface vertically. And if we use this kind of surfaces in power plants, which make the conversion between heat and electricity, then we have surfaces that have much higher heat transfer coefficient, and therefore the production yield and the efficiency is much higher. And we save energy, time, and cost by making these heat exchangers much more efficient than the typical ones. Now, we're passing to the main object of this Erasmus project, which is how to use this kind of smart, advanced, functional surfaces in order to tackle water scarcity. Here I have a generic graph which shows that a lot of places in the earth, not only Africa, which is a common place, but also other places have very bad data about the water availability. So you can see here that 40% of the global population faces water scarcity. This percentage would go to 60% by next year, and 66% of the global population lives in conditions of severe water scarcity for at least 1 month. So how can we use these new materials in order to change this? One of the ideas that we have been developing and working on is to harvest the water existing in the atmosphere. Actually, atmosphere is a huge reservoir of water containing several liters per cubic meter. So if we use this kind of surfaces, the rough surfaces that I showed you earlier, in both modes, hydrophilic, hydrophobic, super hydrophobic, or super hydrophilic, we can have increased collection rates compared to the untreated surfaces. Here you can see that the untreated surface follows this line, and the super hydrophobic one follows this line, collecting much more water compared to the untreated one. If we now go, this is the measurement about dew. So from the water collected using a phase change phenomenon, and includes nucleation of the water on the surface and then collecting it. If we now go to more moist, let's say, regions or islands or coastal regions in which humidity is much higher, and we use this kind of surfaces, we again take an advantage of using super hydrophobic surfaces by collecting much more water compared to the untreated ones, as you can see here, the blue and the red. And of course, in this case, the value of the water collected is much more higher compared to the dew. This can be further improved if we try to, let's say, design better this kind of surfaces. So we have done some first work, and we are working on this on a new project on how to further optimize the collection efficiency of water existing in the atmosphere, either in dew or fog. So here we have tested several designs having biophilic surfaces, so both superhydrophobic and superhydrophilic areas in different concepts, one with spots, one with parallel lines, and one with triangles, hydrophilic triangles inside superhydrophobic background. And we saw that depending on the type of atmospheric water harvesting, we need different type of surfaces. For example, in dew harvesting, we found that the most efficient one was the one with the parallel channels, superhydrophilic, superhydrophobic, superhydrophilic, superhydrophobic. And if we try to visualize this, you can see that in the superhydrophilic parts, there is a continuous film formed that enables water to be collected, whereas on the superhydrophobic areas, we have dropwise condensation that also provides some water to be collected. On the contrary, when we were on the fog collection, we saw that this kind of surfaces did not exhibit the best results. And we needed a surface that had much more ratio of superhydrophobic background instead of having equal, like the one here. So in this case, the best results came from just superhydrophobic surfaces because we wanted to capture the water drops existing in the atmosphere and just move them quickly to our container, or the spots in which the value was much higher. We attribute this phenomenon that in such cases we have excessive moisture coming. So in order to capture a lot of water of this moisture, we also need some small traps in the form of circular shaped superhydrophobic areas that can enable these kind of surfaces to improve their efficiency even compared to the entire superhydrophobic ones. And this is the project I was telling you about. So we are trying to use an easy to implement technology, which is hot embossing and create micro and nano textures, and then create biophilic surfaces of different shapes, different designs, different ratios, in order to have the optimum surface for dew and the optimum surface for fog, and incorporate them inside a single device that can be then scalable to larger devices that can be installed in remote areas and provide several liters of water per day. The next application of functional surfaces is to use technologies related to transforming commercial membranes to superhydrophobic ones, like the ones you can see here. So we have three types of commercial membranes. This one is PTFE 0.1, which has the smallest pores, let's say. This is the same material with slightly larger pore, and this is cellulose acetate, which is a hydrophilic material that is not intended to be used for water desalination. So by texturing or adding top layers by nanofilaments, you can create superhydrophobic membranes, and going from this kind of cases to this kind of cases. In this way, you achieve to enable the antifouling mechanism. So when you try to make a distillation, a water desalination, you have several things sticking on the surface of the membrane. So if this material is stuck on the surface of the membrane, the flux performance of the membrane decreases. So by making them super hydrophobic, you make the membrane, let's say, anti-fouling, self-cleaning, and you improve the efficiency of the desalination. And here you can see that compared to the untreated membranes, we have a flux increase if we make them super hydrophobic. And most importantly, this is the most important part, we manage to have stable, let's say, behavior even after adding a foulant on this kind of membranes. So if we take the untreated membrane and we try to accelerate the phenomenon of fouling, and by adding this protein, we can see that after a short period of time, the membrane is covered with this foulant. Whereas in the micro-nanotextured membrane, you can see that the pores of the membrane are not clogged, and the antifouling properties are sustainable. In this way, you extend the stability of the flux, which is a metric of how efficiently desalination works, instead to the untreated membrane in which flux significantly decreases over time. And of course, new systems have been developed using this kind of technologies. Here we have a filter that can make separations in microfluidic CD systems that are stuck together and have very large yields. Or you can have tubular membranes instead of flat membranes that can even perform better compared to the flat ones. And this kind of material or micromaterials, nanomaterials, because the size of the pore of these membranes is in the order of several microns to some nanometers, are already in use in several applications. And of course, we can also use this kind of membranes or commercial, again, membranes that are sprayed with some nanoparticles in order to separate water and oil emulsions. So have the oil separated from the water, or clean the seawater by spoilage. And as I told you in the beginning, of course, we can use the same functionality, which is wetting control, in order to control the pathogens adhesion on surfaces. So by adding this this micro nanotopography, we can see that we can reduce the coverage of bacteria in this kind of surfaces. So if we have untreated PMMA, we have a very high coverage of bacteria solution on the surface. So the bacteria stick on the surface and stay there. Whereas if we use super hydrophobic surfaces, even after 48 hours, as you can see here, or even after 74 hours, you see that compared to these two surfaces in which the bacteria coverage percentage is really high, in the super hydrophobic surfaces, the bacteria solution is very difficult to attach. So it remains antibacterial even after immersing this kind of surfaces for 3 days inside the bacteria-containing solution. And if we want to visualize this result, here is a super hydrophobic surface. You can see only some bacteria as red marks, whereas on the commercial surfaces or the untreated ones, you can see biofilm formation. And of course, this has many applications in commonly used surfaces or food packaging applications. One interesting observation in this is that instead of having metals or metal nanoparticles fighting the bacteria and eliminating them, there is an interesting micro and nanomechanical effect about the bacteria. So if you have a very sharp topography on your surface, you can kill the bacteria just by a mechanical killing effect without adding any toxic metal, any other antibacterial agent, anything else. So you can see here that the surfaces which have only this micro and nano roughness can, after 24 hours, kill all the colonies existing on them and have the same behavior like the ones that are covered with a copper film in order to improve their bactericidal action. So micro and nanotechnology also enables a new type of environmental friendly materials that only have these micro and nano features that mechanically kill, like knives or darts, the bacteria without adding any other substances that can be considered as toxic. And here you can see some SEM images of the effect. So you can see that we have this micro and nano topography, and you can see the deformation and the complete destruction of the cell when they come in touch with this kind of surfaces. Nowadays, we are also working on this application to change the pathogen and check again about the antipathogen, let's say, behavior. In this case, we used two types of surfaces. One commonly used metal surface, which is aluminum, and the commonly used polymer surface, which is PMMA. And as you can see here, by transforming the surfaces to superhydrophobic, we can, except bacteria, also control the fungi proliferation rate on this kind of surfaces. And no fungi cells was observed on these very rough surfaces compared to the untreated one, in which you have already some fungi cells attached on them. Other works also worked with nanoparticles, as I said before, or other metals like silver. And again, they saw the same effect, that by adding micro and nanotopography and by adding bactericidal action, you can have a significant decrease in the number of colonies existing on this kind of surfaces. So if you compare this, in which we have the CFUs per gram, and it is constantly increasing, if we use a high concentration of silver, we have a significant decrease. For Listeria, for E. coli, again, the same here by using nanoparticle forms. And here I have a table that lists some commercially available antimicrobial materials that are used in food packaging, and some other materials also used in polymeric matrices for food packaging of apples, shrimps, ham, fresh sausages, salmon, pork slice, etc., and use nano or micro functional, let's say, shapes in forms of nanoparticles or other type of thin films. So that is all for today. I wanted to show you that the application of micro and nanotechnologies can provide a wide range of different functionalities. You can control the optical properties, you can control the wetting properties, you can control the protein, cells, pathogens, adhesion or repulsion. And in this way, you can change, let's say, the properties of the starting material, make it on demand, responsive to different stresses, to different probes that you want. And of course, we can use this kind of surfaces either to improve state-of-the-art processes of desalination of water or membrane distillation of water, and of course, propose and expand the use of new technologies like the atmospheric water collection example I showed you earlier. So another critical thing is that new materials, new technologies, new methodologies, new processes can enable us to find new ways to produce fresh water. And one of the scopes of this project is to, let's say, accelerate the uptake of such processes, inform people about such processes, and also improve the state of the art of the technology by itself. So thank you all. I will stop share. So I don't know if there are any questions. Sebastian, do you remember the next week lecture? Just to tell the people in order to
Yes, of course. Yeah, but to start, any questions so far? Anything anyone from the audience wants to ask you? Seemed to be the case. Seems you've been very clear and very convincing. So the next lecture will be on Monday 13th, starting at 8:30 Central European time, 8:30 Central European summer time. And this will be the first part on desalination. So fundamentals of reverse osmosis, electrodialysis, desalination, such basic parts. And yeah, so as a first start, and we'll then continue on Thursday next week with more thermodynamics and more in-depth parts on the desalination.
And of course, for anyone interested, maybe if you have it available, I can also send the link of the project in the
yes,
chat.
Of course.
In which we have the complete. I found it. I can do it.
Okay. If you have it ready, otherwise I have ready the sign-up form for.
So here is the link of the project. So you can see. The program for the next lectures, and of course everybody is welcome to follow, the news of our project. And thank you for joining us today.
All right, then thank you everyone, and have a nice, early weekend. But given that in some countries at least it's a holiday, enjoy if you have the free time, and see you maybe next week then.
Yep. Bye.
Nothing.
Thank you.